So that was a story about petrochemicals, and petrochemicals are very much the traditional home of catalysts. But now a story about how we're moving catalysts into making fuels. So as a globe, we have really an insatiable appetite for liquid fuels. If we look at global figures, as a planet, we use 90 million barrels of liquid fuels every day. So liquid fuels are things like petrol, diesel, kerosene, 90 million barrels every day. To put that into context, that's 2 litres of liquid fuel for every man, woman and child on the planet every day. A big pop bottle of liquid fuel for everybody every day, about 4 pints. A huge amount of fuel. And there are 2 facts which are absolutely certain. One is fossil fuels are a finite resource, and if we keep using them at the present rate, one day they will run out. The second fact is that there is a link between rising global temperature and CO2 emissions, and a large part of those CO2 emissions come from burning fossil fuels. So we need a better way to provide these liquid fuels, and the best way we have so far are using biofuels. Rather than digging our fuel out of the ground, we grow the fuel. Look, even the video is more relaxing. When people talk about biofuels, they mean 2 things. So, there's biodiesel. Biodiesel dominates the market in Europe and in Asia. When you hear stories in the newspaper about a chip shop that's taking their used oil and converting it into a fuel, they're talking about using biodiesel. The technology is very well established. Much more difficult is to make biopetrol. And in the US, biopetrol, or biogasoline, I guess I should say, dominates the market. And the US are big users of gasoline. Now, the biosustainable material, the biofuel that we use as an alternative to gasoline at the minute is bioethanol. So exactly the same sort of ethanol, the same sort of alcohol that you get in a bottle of vodka or a pint of beer. But actually, ethanol is not a good fuel. Its energy density is lower than that of petrol. It's about 70% of that of petrol. That means that if a tank of petrol will take you 100 miles, a tank of ethanol is only going to take you 70 miles. Ethanol is also surprisingly corrosive to engine components, and I can show you a slide to demonstrate that. So here is a solution which is a mixture of ethanol and standard petrol. This is about 15% ethanol. There's a bit of dye in there to make it pink so you can see what's going on. And we've got some aluminium plates in there as well. So these aluminium plates represent the components you might get in an internal combustion engine. And if we heat this solution up to 100 degrees for 20 days, not unrealistic conditions for what would be going on in an engine, this is what happens. This is 15% ethanol. If we use neat ethanol in the same conditions, that's what happens. And I don't know about you, but I don't want my beautifully engineered flat 6 boxer engine to look like that. So ethanol is not a good fuel for a number of reasons. Actually, a much better fuel is butanol. Butanol is another type of alcohol. It's got a slightly longer hydrocarbon chain. And because it's got a slightly longer hydrocarbon chain, it performs much more like standard petrol. Really, butanol is just a drop-in replacement for petrol. You can run any of your petrol cars on butanol and they would run absolutely the same. The problem is how we make butanol. So butanol is quite difficult to make. And we can use fermentation to make butanol, but it's very difficult fermentation. So the maximum strength of a bottle of wine is about 15% alcohol. The reason it's 15% alcohol is that ethanol is a toxin for the yeasts that are producing it. And you get to about 15% and that ethanol will kill the yeast, it's over. Butanol is a far more acute toxin. We can only get up to about 3% butanol and the microorganisms are dead. So it's a very low conversion, it's a difficult, we have to use a bacteria to do the fermentation. It's not selective, It doesn't just make butanol, it also makes acetone and ethanol. And basically, it's just not economic to use these fermentations to make a fuel. So we've got a fundamental problem here. On one hand, we've got butanol, which is a fantastic fuel, but really difficult to make. On the other hand, we've got ethanol, which is a very poor fuel, but very easy to make. I mean, we've known how to do brewing since antiquity. We could make ethanol very easily. So our solution to this problem was to say, well, what we really need to do here is to be able to transform ethanol into butanol. We need some molecular alchemy here. How do we do that? Well, we use a catalyst. Actually, it looks, for the organic chemist, this looks a very simple reaction. In fact, I can tell you this is a very difficult reaction to get to go selectively. We did find some inspiration from a very old chemical reaction, over 100 years old, a reaction called the Gerber reaction. For the chemists in the audience, this is the mechanism of the Gerber reaction. And I think the organic colleagues in the audience will recognise the problem with this reaction. And that is the bottom step here, where we're losing water. Because this type of reaction, it's called an aldol condensation, is notoriously difficult to control when we're using ethanol. We get a whole mixture of products. So again, the problem is one of selectivity. It's a problem of making butanol on purpose. But I don't want to talk a lot more about the chemistry of this. I thought it would be interesting for you to actually see what goes on in the lab. So now, via live video link, we're going to go to the WAS group on the 5th floor of the Synthetic Chemistry building. So hello WAS group, are you there? Okay, here they are. All working very quickly here. They must want to get over for the wine reception, I think. So we're going to talk about chemistry making ethanol and turning that into 1-butanol. So Kristen and hard work there. So here's Richie's beautifully manicured hands. Here's the orange powder is the catalyst going in. It's based on ruthenium. Maybe a second component for the catalyst as well. So this is sodium ethoxide. We're just going to drop a stirrer bead in there. So this allows us to stir up the reaction. And this reaction is going to generate some pressure. So we need to put this in a stainless steel vessel that will contain this pressure. You can see Rich has done this many times before. He's very quick. I'm just going to put the final sleeve on now to make sure everything's sealed up. And there we go. So now we need to add some ethanol to this vessel. So we're just going to open this up, get a syringe full of ethanol that we can buy from a chemical supplier, and that ethanol gets injected into the reactor. And then we need to seal that up, and we need to heat it for a while. We need to heat it overnight. So he's just going to put it into the stainless steel block here where we heat it up, and we leave that overnight. So you can see the beautiful view we enjoy from the chemistry department. Night falls as we're leaving this. Of course, the next morning it's raining. If you look carefully, you'll probably see me just walk past with my morning coffee. There I go. Okay. And now Richie, he's opened this up, and we're going to see what's inside. So, it's stuck there. So he's just going to open this out and put the contents into a vial. And now what we should have is our catalyst, which remains unused, but we've got ethanol, but also some butanol in there. So we need to work out how much butanol we've made. And to do that, we use a technique called gas chromatography. This just tells us how much of different compounds we've made. So this sample gets injected into the machine there, and this gives us peaks that correspond to different compounds, different chemicals. So there's the peak for ethanol, and then we've got this very large peak which corresponds to butanol. We've converted the ethanol into butanol. And you can see there's very little else on the trays. This is a very clean reaction, a very selective reaction. In fact, in terms of the products here, this is 99% selective for making butanol. So we're very excited about this project. I mean, what we have here is the world's best catalyst for making what's likely to be petrol in the future. And needless to say, there's been some media interest in that, we've got industry interested in that. Only yesterday I took a phone call from the Iowa Corn Growers Association. You may laugh, they grow a lot of corn. The arable land of Iowa is greater than the arable land of England and Wales put together. They produce a quarter of all of the bioethanol in the US. So they're very interested in technology that might make a better biofuel than bioethanol.